Hey, today we're doing Codeforces Round 738 div 2. And I'm a little bit late, but let's get started. Move this here. I think you just end up with the entire array. So basically, okay, let's retest. Squares, each of them can be painted red or blue. Oh, I see. Okay, so BRB. What is F? Oh. I got 601. Fortunate. Can you just add scree, try them? I feel like that should work. See. Okay. Okay. Something like this. Just find the first, this one. Here. And if there's none, you just do that. Yeah, okay, so that's easy. Oh, they solved E very quickly. Okay. So thanks. Okay, look at E. Okay, once we install that, installs. Recognize between L and R. M. Just. Oh, okay, so. So you pi on the GCD, I think. Yeah, you pi on the GCD. PI GCD and what? Higher bound is just how many ways are there to not exceed this bound per each, and then oh, you're just multiplying polynomials. Okay, so yeah. Wait, are you just doing 50 NTTs for each of those? That sounds too slow. 50 NTTs because you're no, you just do a knapsack. Just do a standard knapsack. Yeah, okay. Oh no. Okay, yep, looks good. It's equal 0. I didn't read an LR. It has to be ceiling div. I think they're just both ceiling div. So if this one is 3, you just yep, they're both ceiling div. So we get the knapsack. Okay, cool. So maxsum m. This m is the maxsum. And accumulate. And I don't print total. Oh, what? What? Oh, oops, because you can't use that one. Now D2. I have 1 point ahead, Kevin. One point ahead. All right, let's go. D2. think I want to know. Okay, I know the components for each. If I know the components for each graph, now what do I have to do? Yeah, so you just look this code. You can do anything in this code, it's anything not in this code, which means there has to be something, right? You can always find something unless one side is only one component. So if this is what just do something randomized. I'm gonna try that. No, this is not the same. So maybe I'm just trying to grab a random component. Oh, I don't need this. You just continue until the components are done, because you know it's done. Okay, so Never mind this, never mind this. Wait, how do we implement that? Pick a random component? Yeah, I guess we need ordered set for that reason. So I do need this. Oh, I need to. Wait, what? Oh. It should be two. Should be two. This is horrible code. Horrible code. 939. All right. Let's see how this goes. And it passed in 450 milliseconds. How is that? That seems pretty good. All right, gonna leave it like that. We'll see. I think this has a reasonable shot of working. Because if you got a component, okay, what did I change there? Oh, I added bits in, sure. Okay, we are in first place for the moment. We will see about this algorithm on system test. I think it works. I can try to come up with a proof. It might be tricky though. We'll see. But I'll go over the solutions in a little bit. First, gonna grab some food. Okay, here we go. Let's talk about the contest. So we're sitting in first now, just a little bit ahead of Kevin, and then Geothermal in third, and nice job to Anand sitting in ninth, with a couple usual suspects here as well, Kefa, Maxime, other LGMs. So yeah, we'll see how the sys tests go. I'm especially interested in D2 sys tests because I bet there will be some other randomized solutions. But yeah, we can talk about the problems. Overall, I thought reasonably balanced set. I guess, yeah, this is like a pretty smooth curve here, although maybe on the easier side from A through D1. Definitely D2 is the hardest by a lot. And E, I don't know why it was worth 20 points. It is like, it does take a couple observations, but they're all fairly standard observations for experienced contestants. So definitely a much easier problem than D2 in my opinion. Okay, but let's go through everything. So, all right, problem A, we've got a sequence A of length n. We can select an arbitrary interval LR and then do this type of thing. Basically, this example is a really good way to demonstrate it. So if you have this array A1 through A5 and you pick 2 through 5, the new array becomes this. Basically, you kind of take the array and you like flip it on itself, and that's how you do the ands. So you get A2 and A5, A3 and A4, A4 and A3, A5 and A2. So yeah, it's kind of like reminds you of those like flipping pancake problems. But anyway, we want to minimize the maximum value in the sequence, and can we get the answer? So when we're using ands and we're trying to minimize things, we just want to do more ands, because ands never make a number bigger. Ands can only remove 1 bits and make numbers smaller. So it actually turns out for this problem that the answer is just you take all the numbers in the array and you and them. The reason for that is we only need to use this operation, this LR operation, for intervals of length 2. So for example, when you have A1, A2, A3, A4, A5, let me make this bigger, and you just do the operation, you get A1 and A2, A1 and A2. So basically you can pick any adjacent pair and their 2 values together and replace both of them with their and, right? So another way, a shorthand, and I'm going to write this is, I'm going to call this like 1, 2, 3, 4, 5, and then I'm going to write this as 1, 2, 1, 2, 3, 4, 5. Yeah, so basically I'll give you an example on 1, 2, 3, 4, 5 on how we get the entire array to just be the and of everything. So first we do 1, 2, 1, 2, 3, 4, 5. Then we pick these two. We get 1, 2, 1, 2, 3, 1, 2, 3, 4, 5. And then we pick these two. And then we get 1, 2, 3, 4, 1, 2, 3, 4, 5. And then finally we pick these last two. We get 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Right. And then we just do the same thing going from the right to the left. So we pick these two. Oops. And we keep going, and you can see how we get there. So we would have this, and then finally we'll end up like this. So that's just an example that works for any n. But basically, for the actual code, we're just going to read every number and add them together, and then output the result. The kind of base value or default value for bitwise and is -1, because in 2's complement, -1 is represented as like in binary, it's just 1, 1, 1, 1, 1, right? So that's why we use that number, and that's it for problem A. Yeah, take us a couple observations, trying things out. Although this end result is potentially guessable. You could potentially just guess that this is the answer without figuring out why, but it's good to work through the logic and make sure you understand why. Okay, let's look at problem B. So basically, to long story short, we've got this row of squares, which is a string. The string has B's, R's, and question marks. B's are blue, R's are red, and question marks mean we can pick either B or R. And we want to fill in the question marks so that the number of pairs of adjacent values that are the same is minimized. So in this case here, we can get a minimum of 1 pair that's the same if we fill it out like this. So the first one we fill out with a B, and then after that we fill out with, can make this bigger. After that we fill these 3 with RBR. Okay, so here's a claim I'm going to make. I'm going to claim that for every kind of run or every consecutive group of question marks, we should either fill it out as BR, 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 or we should fill it out as RBR, BR. And the reason for that works like this. If we have a bunch of question marks, and let's say we have some characters in front and afterward, and we try these two strings, there is a chance that one of them, like in this case, fills it out perfectly and we get 0 equal adjacent pairs. And there's also a chance that, for example, we end up with 1 adjacent pair. And that this is if we try both of these. Whoops. If we try both of these, one of them will either land us with 0 pairs or 1 pair. And in the case of 0 pairs, that's obviously the best we can do. In the case of 1 pair, you can make a parity argument where basically there's no way to fill it out with 0 pairs. Because, of course, in order to get 0, we would have to alternate within the question marks. But if we try both, we end up with 1. So then 1 is the best we can do. So yeah, so based on that argument, we can just find every, essentially every run of question marks and then just fill it out optimally. So that's what I do in this code. Basically, I take S. So first I put dots on both sides. And then when I find this loop just finds a group of question marks. When I find that group, I will replace the question mark section with this paint function. So paint just gets us for a certain length of question marks, given that the left char is left and the right char is right, basically the things to the two sides, which would be this and this, we're going to paint it optimally. So first of all, if we have a value for left, we just start alternating from there. And then otherwise, if we have a value for right, we start alternating from there. And if we don't have a value for either, we can just do whatever. We can just do BR, 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 or RB, RB, RB. Either way is fine. And so that fills out each question mark section. And that is the best we can do. And the nice thing is, the question mark sections don't interact with each other, so we can just solve each of them independently. Okay, yeah, so that is problem B. Okay, yeah, let's talk about problem C. So for this problem, you've got n+1 villages and 2 n-1 roads. The first half of the roads just make a path from 1 through n. And then the second half of the roads, there are n roads where basically for every pair of n+1 and a village from 1 through n, there is an edge going either in one direction or the other. And this tells you which direction. And basically after that, you want to find a path that goes through every village exactly once. So you want to find a Hamiltonian path. And you need to figure out how to get there. So we can just do a little bit of drawing here. So let's see. So first, let's start with our path. That's good enough. Okay, and then let's have this be 1, 2, and 4. Okay, and then we're going to have our n+1 node separately on the bottom here. And what we're actually going to do is we're just going to start with this 1 through n path, and we're just going to insert n+1 somewhere in here. So first of all, what we can notice is if this edge is like this, then we're already done. We just take this path, right? So let's assume this edge goes this way, actually, to make it harder, because otherwise we're done. Now that we assume this goes this way, let's look at this edge. Now if this edge goes like this, now we can do 1, n+1, 2, 3, 4, and so on. Right, so then we're also done. So again, to make it harder, let's assume this edge also goes this way. Okay, and then same thing. If this edge goes this way, now we can do 1, 2, n+1, 3, 4, right? So again, we have to assume it goes this way. Same thing here. If n+1 points to 4, 1, 2, 3, n+1, 4. So again, we're going to assume this goes this way. And then finally, at this point, we have 1, 2, 3, 4, n+1. So there's always a way to do this. And we're just looking for the first edge that goes from n+1 up to something, right? And in terms of the code, that's really just what we're doing here. we're finding the first one in the array. One in the array means n plus 1 points to that node. And a nice thing about using find in C++ for this is that if there is no 1 in the array, it will point us to the end of the array, which gives us technically the thing after 4, as if that existed, which is actually the right index we want. And then yeah, it's really simple after that. I just make an array of 1 through n in order, and then I insert this last node at this position. And that's it, I just output it. True means that I'm converting from 0 base to 1 base. And yeah, that's actually the entire problem. This code is super simple, but yeah, it's good to just work through the cases, especially the logic of, okay, if it's this way, we're done, so let's assume it's this way. And then you keep going through and you actually can finish the entire problem that way. Okay, so I'm actually going to talk about E first before I talk about D, since E was actually much easier than D2. All right, so problem E. Basically, we have this definition. We want to make an array A1 through AN, and it's mathematical if all of these conditions are satisfied. For all I, AIs between Li and Ri, the sum of AI is most M, and their GCD is 1. And we want to count how many different ways we can do this, modulo this prime. And you may recognize this as the NTT prime. And N is up to 50, and M is up to 10 to the 5th. And then Li and Ri are also from 1 to n. Okay, so this looks kind of crazy, but this actually turns out to be a pretty standard problem. So first of all, these constraints feel more common, I guess, and this is kind of a weirder one, the GCD of 1. The GCD of 1, the way that you handle this is it's just a PIE, so principle of inclusion exclusion. And you're actually doing a PIE on primes. So this is a pretty common kind of number theory PIE where you're doing PIE on the prime. So it actually turns out you want the Mobius function. And yeah, this basically gives you the PIE coefficients for every number from 1 through n. Yeah, but essentially we're just gonna ignore this condition for now, and let's count how many sequences satisfy this, right? So now we've got our count, but we've overcounted things that have a GCD greater than 1. So what we want to do is, for example, count. Now let's count ways to satisfy these two, where all of the AI are a multiple of 2, right? And we want to subtract that out because whenever all of the AI are a multiple of 2, then we have not satisfied this constraint because the GCD is 2 or a multiple of 2. And then similarly for all cases where all of the AI are a multiple of 3, we want to subtract that out, right? And then similarly for 5, 7, and so on. But now we have a problem because for 6, if all of the AI are a multiple of 6, we've actually double subtracted this, right? We've subtracted it in the 2 case and we subtracted it in the 3 case. We only want to subtract it once, so we actually need to add it back. So we add 6 back. So when all of the AI are a multiple of 6, we need to count that and then add that number back. And we kind of keep going this way. And this is the PIE on prime. So this is why the Mobius function works. For 1, we count it as +1. For 2 and 3, you count them both as -1. 5 is also -1. And 6, you count it again as +1. So this is the kind of, coefficient on the count for this number. And the reason we don't do anything for 4 is we don't have to worry about 4 because we only need to worry about whether things are a multiple of 2 or not. Since 4 is 2 squared, it's not going to factor in here. Okay, so now that we know, we have all these values, we need to basically we need to compute, let's say for a value g, how many ways are there to set up AI to satisfy these, where all the AI are a multiple of g. Well, if all the AI are a multiple of g, what we can do is, first of all, since AI is going to be bi times g, then their sum has to be at most m divided by g. And then we can also convert these ranges li, ri to ranges for AI equals bi times g, we can convert that to a range for bi. And so we just do that. It's pretty simple. Yeah, so this is the g, we're checking the Mobius, and then this is the converted range of li ri for the ai equals bi times g for the bi value, and then same thing, m divided by g. So we can actually take the floor again. In this case, this is ceiling division and this is floor division. So you need to be careful with all 5 ones here. And now this solve function is basically solving the original problem here, where if ai is between li and ri, and ai is sum to at most m, how many ways are there to set that up? Here I've converted li r to half open intervals instead of closed intervals to make things a little easier. Yeah, so first of all, let's just get rid of the li, because I mean, we know that that's the minimum. So first of all, instead of being li ri, we're going to convert every range to 0 ri minus li. And then we need to subtract li from m. So we're going to do all that. If m ends up negative, then obviously there's no way to do this. Otherwise, we're just doing a pretty standard knapsack. And when we're doing a knapsack and we include the next number, which can be from 0 to k, we're doing kind of like sums of size k on the previous knapsack table into the new knapsack table. So that's what we're doing here. We're getting the prefix sum array. And then when we compute the new ways, we're just taking a segment sum of length, in this case, r, which is the value ri minus li. So this is a pretty standard DP. I actually almost started using NTT before I realized that you don't need NTT for something this simple. You just do prefix sums and you take segment sums. I also think NTT would TLE here. And then lastly, once we're done, we just take the sum of our knapsack array, because any sum up to m is valid. We could also solve this problem for sum exactly m, and then we would be handling this differently, and also handling this differently. But in this case, it's only up to m, so we just take the sum, and then we return that. Okay, so that's all of the code. What's the time complexity? Well, the runtime of this part of this function, it's going to be n times m, right? Because all this knapsack DP is m time, and we're doing this in n iterations. So n times m. But m here is changing the whole time, right? We're getting m over g. And now this is where, for the whole problem, the time complexity, the harmonic series comes in, where basically if you sum up m over g for every g, you actually get m log n. And this is true even though we're excluding some of the values, it's still m log n. So the overall complexity is going to be n times m log n. So it's going to be 50 times 10 to the 5th times log 10 to the 5th, and that is plenty fast in this case. Yeah, I think my runtime was 124 milliseconds, very fast. Okay, and lastly, let's talk about problem D. So problem D has 2 parts. The only difference is the constraint on n. So in D2, n is up to 10 to the 5th, and in D1, n is up to 1,000. So on this problem, you can explicitly do n squared. On D2, you cannot. Okay, and the problem is just you have 2 graphs. One of them, or both of them, are forests, and they want to add edges to the forests, where after adding edges, the graphs are still forests, so you don't want to create a cycle. And then they have to add the same edges. So if you add UV to one forest, you have to add UV to the other forest. And you want to add the maximum number of edges, and then also decide, help them decide which edges to add. So pretty simple input. We're just going to go through and read all the edges, and then output the number of edges, and then output the list of edges. Okay, so first of all, for D1, since n is only 1,000, we can try all n squared edges. And then the question kind of comes in, does the order that we try the edges matter? Should we do some sort of greedy for that? And this is kind of tricky, but it turns out that the order does not matter. The reason is basically, it turns out that as long as both graphs have more than one component, so at least two components, there will always be a new edge that you can find. So, and in fact, you can make an even stronger claim where you can pick either graph and you can pick any component, and there will be an edge involving one node from that component. So let's take our, I can make a straight line. Let's take our two graphs. So let's divide them into components. So maybe like, now I'm drawing like a face. Maybe this graph has these components, and I'm just like making nodes in the components. This graph has some components. This one has some components. All right. Okay. And yeah, basically each circle is a component, a connected component, and then we're finding ways to connect a pair of components here that also connects a pair here. So let's think about all the nodes. Let's just pick this component. Let's think about all the nodes from this component. There are two cases. In one case, all of the nodes in this component end up in a single component on the other side. So in other words, this component is like a subset of this component, let's say. Let's just put some more dots here. In that case, we can actually pick any node that is not in this component. Pick any of these components, and let's say pick this node, and we can connect one of our nodes from here, which is also in here, to that node. And then this node is going to end up in some other component here, because we've already said that all the nodes in this component are here. So that gets us an edge. And then in the other case, the nodes from this component are in at least two or more components over here, right? So maybe the nodes in this component are in here and in here, right? Well, then it's actually also pretty easy. We can just pick any node in any other component on this side. So let's just pick this node. And when we look at this node on this side, it's either going to be not in this component or it's going to be not in this component, right? So for example, if this node is in this component, we can pick a node from this component that is also here and connect them. So obviously, this connection will be good. It will not be from the same component, and then this connection will be good. It will be not from the same component. So I'll give an example of that. Let's say this is node 3, and this is node 4, right? And like 3 is somewhere over here, and 4 is somewhere over here, okay? And this is node like 8. Okay, now where is 8? If 8 is here, then we're going to do 8 and 4, right? And that will connect these two components and these two components. If 8 is here, we can do 8 and 3, right? And that will connect these two and these two. And if 8 is somewhere else over here, we can do either one. It doesn't matter. So we can always find another edge. Okay, so that proves that we're basically going to find edges until at least one of the graphs ends up with a single component, so it ends up connected. So we actually know the number of edges we'll need to find. It's just the minimum number of components between the two minus 1. And that also proves that we can just try all of the edges and connect them, because, of course, if we try all the edges and connect them, we will end up in the case where we have just one component left. So that is the solution for D1. D1 is quite simple. You just set up union find, you set up the graphs, and then you just try every edge. If it's not connected here and not connected here, then we add that edge and set up unite them in union find. And we just output that. Okay, so pretty simple n squared. And yeah, this handles D1. Now what do we do about D2? Okay, for D2, it gets pretty tricky. We want to find these edges, but we can't consider all n squared. So as I was thinking about this, I was thinking about, okay, what if we just try random pairs of edges and see if we can add them? Because we have a nice algorithm from D1 to decide whether we can add them, right? We just see if they're not in the same component, on both sides. So very efficient. And it turns out that could be a problem because there can be cases where there's literally only one edge that works. So to give an example here, let's say we have two components on each side. In the first side, we have just one by itself. And then here we have 2 through n. And then on the second side, we have just n by itself. And we have a component of 1 through n minus 1. And if you think about this, what you'll find is that the only edge we can add is 1 to n, right? The reason is if we pick any number between 2 and n minus 1, we'll just run into a problem where the two nodes will be in the same component on at least one of the sides. So there's only one edge out of all possible edges that would work here. I guess we can make it clear this is a component. Yeah, okay. So I ended up modifying my algorithm. Instead of picking a uniformly random node, what I actually do is I pick a uniformly random component from each side. And then I pick a random node from each component. And then I try to connect those two. And so you can see in this case, that has a high probability of succeeding. You just have to pick this on this side and then this on this side. So the chance of succeeding is at least 1/4, just 1/2 times 1/2. It's actually slightly higher than that because you could pick n here and 1 here, but we can basically ignore that. So we can just say it's 1/4. And getting into a proof here it's fairly complicated, but just to try to give a high-level overview. What we actually want here is we can think about it like this. We pick a component here and we pick a node here, right? We pick a component here, we pick a node here. Let's think about the node we picked here. Well, it's going to be in one of these components on this side. And if we kind of reorder the way that we pick, let's think about picking a node here first and then picking the component on this side. Well, that means if there's x components on this side and there's y components on this side, there's only a 1/y chance that we collided the component on this side. So no matter what node we ended up with on this side, there's a 1/y chance that we picked the same component as that node on this side. Similarly, there's a 1/x chance that we picked the same component as whatever we picked here on this side. So essentially our probability of succeeding is going to be at least 1/1 minus x, sorry, 1 minus 1/x minus 1/y, right? So if either of x or y are bigger than 2, then this probability is very significant, right? It's at least 1/6. And then, so there's only a special case when x and y are both equal to 2. And you can work out some details here. Basically, you can show that there's actually a additional plus term here, which kind of is the essentially the double overlap term. So this is the probability that when you pick on both sides, that both components overlap. So when x and y are 0, or sorry, when x and y are 2, this value turns out to be 0, but this double overlap value turns out to be a significant probability. So essentially, in all cases where x and y are at least 2, there is a non-trivial probability that we end up with a workable edge, and that probability is at least 1/6, and potentially even, I think it's potentially even better than that. I think it's at least 1/4. But regardless, as long as it's at least some specific cutoff, it's going to be this algorithm will work with high probability, or not even high probability. This will work always, and the runtime will be fast with very high probability. Because essentially, we're just flipping a 1/6 die and doing it again and again until we hit the one we want, and then we continue. And we only need to do that potentially the number of times is the number of components. So there's some implementation details here. Basically, the way I set this up was, so first of all, I calculate, okay, I know I need to add this many edges. It's the min number of components minus 1. And I added to the union find, I added for each component a list of the nodes in that component. And set that up here. And then the other thing is when you unite, you merge the smaller list into the bigger list. Or you just insert the smaller list into the bigger list. And the standard smaller to bigger idea, this will take n log n time in total. And then that helps us pick a random node from a component. And now we need to pick a random component. The way I did that was to just set up 2 ordered sets. These are BSTs where you can find a specific index. And so basically the way that I get a random node is, well, first of all, I decide randomly between the 2 components, and then I find I pick an index out of the number of roots, the number of components, and then find that root. So this will be a random root or a random component with uniform probability. And then I pick a random element from that root's list. And that is how I get a random component and then a random node from that component. And yeah, basically I just continue until I find enough edges, generate 2 random nodes with this setup. And it's possibly that you don't actually need to do it quite like this. I could have just done a random node from the first side and then a random node from the second side. But it doesn't really matter because either way, even if you pick 2 nodes from the same side, you might as well just try them. It doesn't really hurt. And you have a 1/2 chance of picking the 2 different sides when you do that. So this is actually not necessary, but yeah, basically use the same criteria as before. Make sure there are different components on both. If so, we add them to edges and we unite them, and then we need to update roots. So this is a slightly tricky thing, but basically I erase A's root, I erase B's root, and then I unite, and then I add the new root. And then we just output. Yeah, and so this has an expected runtime of n log n. The reason is because we should only have to do O of n iterations of this loop. And once we are done with that, or once we find that, basically each of these operations is log n time. And then similarly, this smaller to larger merging is also n log n time. So overall, it's going to be n log n, I guess, plus the union find time. Okay, so that is it for this round. D2 was definitely the hardest problem by a lot. I believe there are some good non-randomized solutions as well, and curious to hear what other people did for this problem. Our system test underway. Let's take a look. Okay, it looks like it's all in pending. Okay, so we'll see how system tests go. I would say I'm pretty confident in my D2 solution, but don't want to claim too much before it's all done. So we'll see how that goes. But anyway, thanks for checking out this video. If you liked it, please subscribe to get notified for more videos. And either way, I'll see you in the next one.